All right, I think you can see my lecture notes. If I'm monitoring the chat, so if something is unclear, um, just say something, or if things are good and visible, also give me a thumbs up. Like right now, everything is, you can see the screen when I scroll, you can see me scrolling, right? Is that a thumbs up from someone would be good. Um, okay, so um, today we're going to talk about Bayesian statistics, but before we get there, I just want to make sure that we're all on the same page in terms of probability language. Um, I took my probability course, first probability course, long time ago, and back in the 90s in Odessa. But unfortunately, I don't remember any terminology in any other language than English. So and that's why I wanted to kind of go with you over terminology. In case something looks unfamiliar, please speak up. I will not be able to translate into Ukrainian necessarily the terminology, but I will just explain it in a different way so that you probably recognize it. Um, Okay, so let's start with just random experimentary process, right? So it's actually quite philosophical what we call random and what we call deterministic. I don't want to go into philosophy, but even a coin toss which is, a classical example. You're tossing a coin and you decide which side the coin falls on, heads or tails. The head and tails, I apologize, I will have to use this because it's so standard. It's not necessary. It's only makes sense if you have a head of someone on a coin. So heads means one side and the tails means the other side. But even the coin toss, it's actually quite surprising. Why is it stochastic? Technically speaking, if I know my physics, which I don't, but someone who knows physics should be able to calculate and predict quite precisely which side the coin will fall on. The problem with this coin toss is that it's an example of a chaotic dynamical system where the initial velocity, because we cannot control it with our fingers very well, even small perturbation into like how quick, with the force we apply to the coin toss, that changes everything. And so it's even though it's a perfectly deterministic system, if I knew how exactly what force I apply with my fingers to toss a coin. In practice, it's probabilistic because we cannot really measure or control our force very well, the force of coin toss. Anyway, so this is just an example of a random event which generates simple events, either heads or tails. These simple events, we can start combining them into other events. For example, if I toss a coin twice, I can have two heads, one head, one tail, one tail, one head, two tails. Those are simple events. Those are all possible outcomes of this random experiment. And so that's what, we call them, all of these events, we call them together, a union of them, a sample space. So in this case, a sample space just has four elements, these four outcomes of the experiment. But events do not have to be simple. So we can combine them. For example, I can start making statements about other potential events. I can say, okay, what about uh, the event which says at least one head, right? So uh, if I do that, I can just list all simple events in which this is true, right? Head contains at least one head, head tail, and tails heads, right? So this is an example of not a simple event where we say at least one H or at most one H. Event B will be um, heads, tails, heads, and two tails, right? So this is an example of how we can form more complex events. And as you can see, maybe remember, I hope remember that, you can think about events in terms of set theory. So really they're subsets. There are certain rules that we want from these subsets, but for now, I will omit most of the technicalities. You can think of them subsets. So that's why it's very useful to think sometimes about these Venn diagrams when we think about overlaps, right? So this is sets A and B, the ones that I just wrote out a second ago, I drew them on a on a plane as dots, and now I have and I highlighted A uh, with an ellipse and the B with another ellipse with the blue one. Okay, so what we can say, a useful concept is mutual exclusive events, which just means disjoint in terms of set theory, right? So these sets are not mutually exclusive. They can appear at the same time. But for example, if I have heads and tails as in my outcome, this one, right? This belongs to both event A and event B. So these two events that we just talked about are not mutually exclusive. You can also do very, as usually with the set theory, you can do the same arithmetic. So when we say events A or B, we really mean a union of two sets A and B. When we say A or B, we mean, and B, we mean intersection of A and B. And a complement of an event or set is just, again, all not something that is not an A, or everything that's not an A, sorry. Okay, so this should be all a review, because I'm assuming you know probability. If you don't know probability or you haven't not seen this at all, the probability, it will be hard to jump right away into Bayesian statistics and do it in four lectures. But I just want I want a little bit of a warm up at least. So if we go through this arithmetic real quick, right? So we've talked about before. So this is our event A that we already had. I don't know why I erased this part. I didn't have to, but I'll write it one more time. And then event B, we just talked about that. But if I want the union, right? So the union of these two events, in this case, the union really is the whole sample space. So it has heads, tails, heads, and tails. So everything is included. So this is the whole state space, or sample space. Sorry, sometimes in stochastic processes, we usually use state space and probability sample space. So I apologize if I sometimes say one versus another. I should not use them interchangeably. I should just stick with one, but sometimes the habits may kick in. Okay, so intersection here would be, right, the intersection we talked about. This is during this picture, it's really easy to see the intersection. The intersection are these two events in the middle, HT and TH. So this becomes this event when we basically when we toss a coin, we get exactly one heads and exactly one tails outcome. The complement of the A is TT, and the complement of B is HH. Again, because I'm including basically HH is the only event not here, and TT is the only event not here in this in the event A. Okay, are we good so far? Ask away if something is not clear, because I definitely don't want to lose anyone during the warm up, so we can do more interesting stuff later today and during the rest of the lectures. It is surprising that you don't need a lot in terms of axioms about probability. All you need is really to say, okay, I need some function that sends my events to numbers between 0 and 1. So for any event A, which is a subset of my sample space, I want that to be a number between 0 and 1. I want the probability of the whole state space to be, or sample space, sorry, to be 1, which basically means that something needs to happen, right? If I have an experiment, that means that some event needs to happen. It cannot be just a vacuum of nothing happening. That's all, and that by definition means that it should be with probability 1. I should have something. And for mutually exclusive events, if I want a probability of A or B and they cannot happen at the same time, I can just add those probabilities. And it needs to happen for any finite number of these A and Bs. I wrote out just two because it's easier to see this way, but typically, if you open like a probability book, you'll see events A1 up to A sub k, and the mutually exclusive, and the probability of a union of them is a sum of probabilities of individual events. So that's really all we need, and we can, probability, we can develop the whole machinery after that. The conditional probability is, of course, the star of this show for the whole full lectures, because the Bayesian statistics is based on conditional probabilities. So as I'm saying here in the notes, that sometimes we want probability of event, but we also want to condition on that something has already happened. And for example, you can, very simple example, even though it's very, very topical for us here. For example, if my event is being struck by lightning, I'm walking and I'm thinking for some reason, maybe because I'm that type of person, like what's the probability of me being struck by lightning right now? And if I'm walking and it's a sunny day, I probably should say, well, it should be zero, very close to zero, because I don't see any rain or clouds or anything like that. But if I'm caught in a storm, and that's probably one you normally think about that type of event, then that probability goes up, right? So this conditioning changes these probabilities. Conditioning on me being caught in the rain changes at least my subjective probability of how likely I am to be struck by lightning. And as a matter of fact, this is already Bayesian statistics. I will repeat this point multiple times. It's very elementary, of course, but the data that we have here is that I'm observing that I'm caught in the storm, in the rain, right? So that's my data, and suddenly that data changes my I updated my prior beliefs about being struck by lightning. So we'll go over that in a more interesting example just in a second. So conditional probability is defined. So this is just a definition where it's just a ratio. If I want probability of A given B, it's a ratio of joint probability of A and B together divided by the marginal probability of B, where as you can see, because I'm dividing by this, I am requiring that this event has probability more than zero. And that makes sense if you think about it for a second, then it makes sense, because it doesn't make sense to condition on improbable events. So if an event cannot happen, if it has probability 1, why would I condition on it? It makes no sense, because it doesn't make sense to condition on improbable events. Okay. So there's lots of very simple algebraic manipulations that typically we do, and I want to highlight some of them. So of course you can go. Sometimes you have the conditional. If you want to join, you can just if we multiply both sides of this equation by probability of B, you get this equation which says that probability of A and B is a product of probability of A given B times probability of B. You can notice it's because it's on the left hand side is symmetric. We can also flip it and decide to condition on A, right? So instead of conditioning on B, I can say, well, joint probability of A and B is probability of B given A times probability of A. And the Bayes rule kind of just goes one step further. So the Bayes rule is the one that we will use a lot in this course. Basically says, okay, so you have this definition of conditional probability. So probability of A given B is probability of A and B divided probability of B. And then I can use one of these inversions. So I'm going to use this one that I just talked about last. If I use this during that step, then I can say, okay, this is probability of B given A times probability of A and probability of B. And the reason I'm highlighting this, it's very simple manipulation here, but basically the highlight here is that, okay, if you know one conditioning, right? If you know conditioning of B given, you can work out probability of B given A. This little Bayes rule allows you to kind of flip it. You flip the order of conditioning sign, basically, right? So now B used to be on the right. Now, on the left-hand side of this equation, B is on the right side of conditioning. But if you look at the right side of the equation, then B is on the left side of the conditioning sign. Right? So that's useful because of how these probabilities come to us in practice. A lot of times we do need to do that. But just again, the key players in this little mathematical game we're going to play right now here in class, and then in your homework assignment, I'll give you another example so you can practice this. The key players are marginal probabilities, joint probability of two events. There could be, if there are more events, there will be more probabilities, but and conditional ones, right? So those are all things that we can have or compute at any point and so on. Okay. All of you are with me so far?
Uh, I don't know, was it only me or I've lost the sound. I couldn't hear anything. I don't know about others.
All good here.
All good here? Okay. So maybe that was on your side. Okay, that's good.
Okay.
All right. Thank you. Okay. So let's look at this example, which is our first example of Bayesian analysis, although it's very elementary to the point where sometimes you don't have to view it as Bayesian, but I will provide kind of an interpretation toward the end. So the premise is the following. So we're evaluating medical tests for disease D. No test is perfect, and so this particular test has this not problems, but just properties, because all tests have false positives and false negatives. So we will assume that the false negative rate of this test is 1%, right? Which means that 1% of the time, if the person is positive for the disease, the test will say, no, you're negative, right? So it will make 1% of the time this error. And then false positive rate of 2%. Oops. What happened here? We also know that the frequency of the disease in the population sorry, my pen is acting up. Frequency of the disease in the population is very small. It's 0.1%. So it could be that we're testing for a rare disease. Like most of cancers are, luckily for us, are quite rare and so on. It could be that we're doing COVID testing, but during very early stages of the pandemic, where most of the population is disease-free yet. And so imagine we're doing it in kind of like April 2020 or something, or maybe even May 2020. And the question is, what's the probability that that patient has the disease if that test was positive, right? So this is the properties of the test. This is the information we have. I go to the clinic or to a testing site and I get a test and I see a positive result. So I want, as a patient, and I think that's a reasonable question for me to ask, okay, what's the probability that I really have the disease? that the test did not make any, the test kit did not produce false positive, right? So is it clear what we're after? So we have properties of the test. And by the way, the properties I listed are actually pretty standard for a lot of tests. I didn't invent it's completely artificial numbers. I mean, I did put them somewhat arbitrarily. It's not a particular test, but they're not unusual. So the events of interest are, we have an event which T plus, which means that test is positive, T minus test is negative, D plus as disease present, D minus disease absent, right? So those are all possible events. And let's think about what probabilities were given to us. So probability of T plus given D plus versus probability of T minus given D plus. So let's think about that. Here, I would love if it was more interactive, but I don't know, with many people, it's probably hard to do. But feel free to, when I ask something, in order not to, interrupt the lecture completely or to kind of talk over each other, you can simply, I monitor the chat. So if you want to kind of give me some answers in the chat, if it's easy to type, please do, because it makes it more fun for me and hopefully for you as well. So the question here is, do we know anything about these events? So for example, do we know anything about probability of T minus given T plus? So if we think about it, probability of T minus means that the test came back negative, but yes, these two sum to 1. That's correct. I see you're typing this up. And probability of T minus given D plus means that I have a disease, but the test insists that I don't. So it's making a mistake. The only question is it false negative or false positive mistake? Yeah, that we're talking about right now. Right. So the second row is false negative, and we know that from our conditions of the problem. Thank you. I see that Denise said the second row is false negative. So so that means that we know that this is 0.01, and already in the chat you pointed out that these probabilities need to add to 1, so that's why we automatically know it's 0.99. And so we can play a similar game with T plus given D minus, T plus given D plus. So here I have T plus given D minus. That is, I don't have the disease, but the test insists I do. So that's false positive, right? Yes. Thank you. Thank you, Anastasia. Yeah. So this is going to be now, according to our problem conditions, this is going to be 0.02, and these two probabilities that I just wrote, they need to sum to 1. That's why it's 0.98. Okay, so this is so that's good. So we mapped our the problem into conditional probabilities. That's good. We also let me add here the marginal probability of D plus. That's the frequency of the disease in the population. It's 0.001, right? It's 0.1%. So that means it's 0.001. So this is all the information we know. Top left and bottom right are not equal. So the question was why? So because they would be equal. That's a good question. Oh, sorry. Yeah, okay. Yeah, I just wrote it incorrectly. That's why. Hold on a second. Yeah, thank you. Good point. Thank you for catching this. Please do catch these things. Yes, because I just made a typo. Yes. So this is D minus. So this is, I was trying to write out both conditioning that the D minus. Yeah. Yes, the last one should be T plus given D minus. So it means that, hold on a second. What am I doing? Yes, I'm making two mistakes. Sorry. I got too chatty. Thank you. So yes. So this is not a mistake. So this is correct. This is called true negative. So true negative is 0.98, and this is false positive is 0.02. Thank you. Good. I'm glad you're following me. That's good. That's awesome. Okay, so this is all we know. Now the probability that we want to compute is probability of, and let me maybe write it out in blue, probability of D plus given T plus. So I want to know the test is positive. What's the probability that I really have the disease, right? So that it's not a mistake. And so we can start writing out our definition of conditional probability. So this is D plus and T plus together jointly probability of T plus marginally. And when you look at this, it looks a little disappointing because we don't know any of these probabilities, right? So right now we don't have any of that written out as blue on the top. But the Bayes rule tells us we can flip the conditioning, right? So the conditioning on the was before D plus given T plus, but if I do T plus given D plus, well, that I know, and I need to multiply by probability of D plus, and then I need T plus over here. Right, so this is already good news because I have this and this I do know, right? So I'm putting check marks. T plus given T plus, that's 0.99. Probability of D plus, that's the frequency of the disease in the population. I know that's 0.1% and so on. So the only kind of so far unanswered question is this, but it turns out, and it's a typical calculation we'll need to do typically, that when we typically can use a law of total probability to work this out, right? So we can say, okay, probability of T plus, that's a union of two events. So T plus could happen together with D plus, or some union T plus can together with D minus can happen, right? So we're trying to use the calculus of probabilities to work this out. So because only two things can happen, disease can be present or absent, and I'm basically writing out all the possibilities. And notice also that T plus intersection D minus and let me T plus given T plus, let me do this order, and T plus intersection D minus are mutually exclusive. So they cannot happen at the same time. Therefore, if I'm taking the union, I can just add them up. I don't need to do anything else. So it's T plus intersection D plus probability of T plus intersection D minus. Right, and we already did this, so a little bit of that. So we can invert, sorry, so we can inverting conditional probability definition. We basically already have done this, right? So if you look at this D plus and T plus, the first one, we already worked it out. We know that we can compute it because it's a product of two things we already know. So hopefully the same thing will happen with the other. So joint probability of T plus given T plus and D plus, we can work out as T plus given D plus times probability of D plus probability of T plus given D minus, so that's the second term, times the probability of D minus. And, we can plug in concrete numbers. I did this, and you can check me later on this, but I don't want to redo the calculations on a calculator or computer or anything, but let's see that we can plug it in. So the only part that, maybe not obvious, so this part is clear, right? So this is a true positive, which is 0.99. We know this because we kind of worked it out already. So we agreed on that. D plus is probability of the disease or frequency of the disease in the population. That's 0.1% or 0.001 in terms of probabilities. Now, this is our false positive, and that's why I'm plugging 0.02 from this agreement that we had, that this is what it should be. What is probability of D minus? That's the only thing we don't have, but it's on here, but we kind of do. So what's the probability of D minus, if someone can give me in the chat? Or don't even, yeah, exactly. Thank you. 0.99, because it's 1 minus, right? We're using the complement of the event. So if I know that probability of D plus is 0.001, then probability of D minus is 1 minus that, right? So we know what we can compute. And if you plug it in, you'll get something like 0.02 if you round it up. And but that's not the number we wanted to compute. So let's go back to our calculation. So let's finish what we wanted to compute. So back to our calculation. As a patient, you should be interested in probability that you have the disease if you tested positive for it. And so we already said, okay, this is T plus given D plus times D plus divided by probability of T plus, and we worked out now all the terms. So we know this one is 0.99, this is 0.001, this is 0.02 approximately. And in the end, if you do it, you'll get 0.005. Sorry, 0.05. So it's 5%, very small number. So, which should be a little surprising to you, because notice the test is pretty accurate. So the test makes mistakes in one direction 1% of the time, in the other direction 2% of the time. Yet when I get a test, my assessment is that only with 5% chance that this I actually have the disease if I test positive. And the key here is the marginal probability of the disease. So before you become too surprised or confused by why this just happened, it's not a magic trick, so I just want to show you what will happen if we redo the same calculation, but with the probability of the disease being 10 times larger. So still small, but not 0.1%, but 1%. But everything else will be the same. So in this case, the T plus, we will need to change this calculation into 0.01 plus 0.02, 1 minus 0.01. And so that becomes 0.03 now. And then if you plug the same numbers, again, you can check me later on this. And that becomes 0.33. So that's a much larger number. Still small, like it's still not 100% basically, but it's much larger number, right? So much larger number. And so the kind of key here, the key statement here, this is really our first Bayesian analysis, but it's very elementary, but only with events. We're going to do more complex models today and especially in the next couple of days or weeks. Our prior information was that, in this case, that the disease was this. So that means we're kind of assuming that I'm a random person from the population. So if you grab someone from a population, well, the chance that they have a disease is very, very small, right? It's 0.1%, very small. So even if you test them positive, it turns out that's not enough evidence. This data is too weak. If you test them twice, you can repeat this calculation. If you test them twice and condition on them twice testing positive, that will definitely change the picture. But if you test them just once, even with the fairly accurate test, it's not enough data to overpower basically this prior information that the disease is rare, and I should not expect anyone walking with that disease really with high probability. And in this case, when we increase that frequency, now I have a higher chance of grabbing someone at random from a population, and then they will have a disease. That means that these data provides kind of it agrees a little more with the prior, and so our data set allows us to make it more conclusive, basically, or go in the right direction at least. Yeah, so you need to increase. Yeah, you definitely need more accurate tests. I think it's in the comments, Arseny said that you need more, much slower false positive. Yes, you definitely need a more accurate test, but that's frequently not possible. So there's tests have their own limitations in terms of just basic biology, but according to which they work. Okay, so you can ponder on this example more later if you haven't seen this before, but I just want to make a note that this is our first Bayesian inference, and I kind of want you to, the way to think about it as a Bayesian inference is that we started with we started from prior knowledge. And so that was our probability of D plus. We had some information about how frequent the disease is, and updated this prior knowledge. Oops. Sorry. With data. The data was very limited. It just, our data was that T plus was a true event, right? It happened. The test was positive. And arrived at the posterior, what we call in Bayesian inference, posterior distribution, or posterior in this case, probability. Really, it's not a full, well, it's a distribution of a very simple random variable, which is a Bernoulli random variable, but it's a posterior probability P D plus given T plus. But really, it has all the ingredients. Even this simple example has all the ingredients of a proper Bayesian inference for a single kind of discrete event. Now we want to talk, switch and talk about Bayesian inference for kind of more a version that is more mappable to your classical statistics, for example. So in classical statistics, this would be estimating the proportion of in a population from a random sample. So we want to be able to do the same trick that we did with Bayesian inference in this medical testing example, but now I want to be to do it in a for continuous random variables as well. Just again, to remind you, a random variable is just a function that maps events from sample space into real numbers. Could be high dimensional, could be one dimensional. It doesn't really matter. For us, right now, we will deal mostly with n is equal to 1 for now, but not necessarily. We will have multivariate random variables very quickly too. So again, for coin flipping, for example, right, my sample space is these events, but if I map and I count number of heads, that's 2, 1, 1, 0. So on the right, this G function of this, that becomes a random variable because now I have something real, I have some real numbers to play with, right? So that's one way to define random variables. Discrete random variables are typically, we define them using probability mass function. So for each in discrete random variables, you can always, even if they do not take values on non-negative integers, you can still kind of redefine what the numbers mean and still map them on them. But you can have negative ones here as well if you want to, a negative 2. But typically we have k, which is a value of the discrete random variable, could be 0, 1, 2, 3, up to infinity. It doesn't have to stop at n, but here in this example I stopped at n. And then each number has its own probability assigned to it, and so that becomes a discrete random variable. For example, Bernoulli is a random variable which takes only two values, 0 and 1, 1 with probability p, 0 with probability 1 minus p. So probability mass function in this case is defined by just these two numbers that add up to 1. And expected value of a Bernoulli is p, and the variance is p1 minus p, just to remind you what they are. if you haven't seen these old friends of yours for a long time. Binomial distribution is just a sum of Bernoullis, right? So binomial means that, oh, I have lots of Bernoullis and I'm summing them up. It's actually this example, right? So if I'm summing up my heads, that's a binomial random variable. I'm summing up kind of zeros and ones. So it's a counter, right? So when I sum up indicator functions, it becomes a counter when I'm counting something. And so in this case, I'm counting some sort of successes. I can call success head in a coin toss, or I can call success positive test or something, anything I want to call success. And so that means that this random variable can take values from 0 to n, and the probability mass function is defined by this little formula with the binomial coefficient. That's right, it's called binomial. And the expectation of a binomial is n times p, right? Probability of success times the number of trials. N is number of times you do something, number of trials in your experiment. And the variance is n p times 1 minus p. As you can see, Bernoulli is a particular case of binomial when n is equal to 1, quite trivially from this formula. Okay, so this is discrete random variables. Continuous random variables, slightly trickier, but basically, before we go into this continuous, what's useful is that probability mass function is one way of doing it, but we can also define CDF, cumulative distribution function, which is defined like this for any random variable. And what's nice about that, that object exists for any random variable, regardless whether it's continuous, discrete, and no matter how bizarre and weird it is. For continuous random variables, what we do, we define, instead of probability mass function, we define probability density function. These numbers are not probabilities, they are non-negative, but they don't have to be below 1. But they must satisfy this property that if you integrate this density from between negative infinity and x, you get your CDF back. So basically this f is defined via capital F. And for example, we will play today with the beta distribution. So for the beta distribution, it's a particular distribution that lives only between 0 and 1. It has these parameters, alpha and beta, inside of it. And the probability density function of a beta distribution is defined as this, which kind of, if you look at this, it looks a little bit like a binomial. I have x to the power minus x to the power here, p to the power minus p to the power. Normalizing constants are different, so they're different, but they clearly were designed for each other. They're meant for each other. It's a match made in heaven, and you will see in a second why, because they algebraically kind of designed to play with each other nicely. Okay, this is just a quick recap of random variables. Ask questions if some of this language is not familiar. I can try to elaborate a little more. But now, since we now can talk about random variables, we can talk about our first Bayesian inference. And the premise is that, again, it's just estimating fraction of something in the population. So in this example, I just wanted to make it, somewhat interesting in terms of context. So suppose we would like to estimate the fraction of people in Los Angeles who have been infected with SARS-CoV-2. SARS-CoV-2 is an official scientific name of a coronavirus that causes COVID-19. The number 2 is here because the SARS-1 was back in 2003, but it did not spread globally. It stayed mostly in Asia. So this can be done by testing for presence of antibodies that we develop in response to any infection. So this is called seroprevalence study. Basically, we can grab a random sample from Los Angeles, in this case, 100 people, and test, do they have antibodies against COVID or not? If they have, that means that they had it before. Otherwise, they would not develop antibodies. So that gives me a way to estimate the fraction of people who have experienced COVID in Los Angeles by this time point. They may already recovered, but when we recover, our antibodies stay in our bodies for some time at least. Some of them stay for a very long time, for lifetime. So, so that's a way to test basically who already had COVID in Los Angeles by, let's say, whatever, May 2020 or something like that. And so in this case, our data will be, it will be before I observe it, it kind of hypothetically, it's a random variable. I don't know what it is yet. So number of individuals who had antibodies. Good question about the vaccine. Yes, so this would make sense only in the pre-vaccination period. There is a way to distinguish sometimes the antibodies developed in response to vaccine versus to the natural infection. But in this case, I was imagining it was a pre-vaccine study. We did this study here, for example, in not in Los Angeles, but in Orange County where I live, in August 2020. And that was before vaccines were available, so we didn't have to worry about it. But it's a good question. It could be confusing if you have vaccine immunity, induced immunity, and natural infection induced immunity. So good question. So in this case, it's a random sample, so I'm assuming that Y is a binomial with a number of trials is 100, number of people I'm going to test, and some probability theta, which really I don't know yet, but that's the fraction of the people who had COVID. So I would like to be able to estimate that. And so suppose my prior belief is that from other studies, I know maybe that it's somewhere between 5 and 20%. I don't really know what it is. So this could came from studies done in other cities. So in Los Angeles, this study has not been done, but maybe it was done in Chicago, maybe it was done in San Diego, who knows? And we know that these numbers came back, and the cities are different, but not that different from each other. And so that's typically how this information comes to us. It doesn't really come to us in terms of distribution. Someone tells us, you ask scientists or you read yourself literature, and then you kind of form your opinion about what your prior belief is about this number from the previous information that you have. And we can encode this information, code this prior belief using a beta distribution. And so we will say theta a priori is distributed as beta with parameters alpha is equal to 2 and beta is equal to 20. How I came up with this number, you just play with them. You know something about the properties of beta distribution and you use them. Just to jump a little forward. So this is a picture. Ignore the red lines. We haven't gone through the calculation of the red lines yet. But the blue is my prior. It looks a little different because of the scale is different, but it's the same. Blue is the same curve. It's just the y-axis is a little different on the here and here, so that's why it looks different. But it's the same curve. And basically, this is how, this prior says, well, it's somewhere between 5 and 20%. Look, most of the probability mass, right? If I kind of, if I take this 2 points here. Well, hold on a second. This one should be 0.5, should be here, it looks like. So that's a lot of mass here, right? So that's a lot of mass area under the curve tells me the probability that this continuous random variable falls between these two numbers. So this would be my 0.05. And so, I played with it and I chose the distribution. It's somewhat subjective. You can make it a little different. We can do sensitivity analysis later. But that basically, I decided to use that beta with alpha is equal to 2, beta is equal to 20, because it gave me roughly what I wanted in terms of the range of this frequency in the population. Okay, so the posterior belief now we can derive using Bayes rule again. So for the random variables, it works the same way, except it's a joint distribution. It's a joint density of theta and y now. Those are not events anymore. Those are random variables. And so the small y is my data. Small y is here because small y means that's something I observed, right? So you can also think of it as big Y is equal to small y, something like that. And so then we can play the same game and say, okay, I can invert the conditioning y given theta times p of theta, and on the bottom this becomes an integral, right? I can use the law of total probability again, and if you think of this again, it requires. Sorry, I'm relying on you knowing random variable calculations here because I cannot review everything, unfortunately, in just 4 lectures. But this is a typical example, right? If I have a joint distribution of 2 random variables and I integrate one of them out, I remain with the marginal. So that's a kind of a typical probability calculation that we do. And so if we work this out a little more, right? If you plug it in, and I'm gonna start plugging in, but I probably will not have time to do all the tedious calculations, which is probably good for you, that I don't have time for this. I can just post it in the lecture notes. But this is my binomial, right? So this is this is called likelihood function. In this case, it's my probability or density of, in this case, it's probability because y is discrete. Likelihood function, and this is my prior. And so the likelihood in this case is a binomial, which is exactly what I wrote, the formula. And the prior is this, an ugly expression of the beta density. My apologies to the beta density, but I don't think it's pretty. Theta alpha minus 1, 1 minus theta, beta minus 1. And on the bottom, I have this integral, the same thing that I have in the numerator, but I have an integral with respect to theta. You can go through this. I will post the little tedious algebra, but in the end of the day, you can kind of show that the theta given y, when you derive this density, it turns out it will be also beta density, but with parameters y plus alpha and 100 minus y plus beta. So notice our prior density had these numbers, where it is, sorry. Oh yeah, I lost it right here. Alpha and beta, 2 and 20. Our posterior, after we observe the data, we modified this. So for example, if y is equal to 0, which basically means, okay, I had sampled 100 people and I get only 0, then our posterior theta given y would be beta 2, right? Y alpha plus y is 0, so it remains 2, and then 120. So I'm just plugging these numbers in the formula. But if my y is 10, then our posterior will be theta given y will be beta 12 and 110. Right? So that's different, just 2 different scenarios. What would happen if I had 0 people who were positive versus 10 people? And that's exactly what I'm showing you here in this plot, right? I'm having the first scenario where I have my prior and my posterior when y is equal to 0. Notice it when y is equal to 0, it's hard to say anything. It's basically, well, like, is it 0? Well, no, it's not 0 because you may have gotten unlucky. Maybe that's what happened. And so basically my posterior is kind of hugging 0, and it says, well, it's probably less than 5% to be honest, but it's not exactly 0. But if I had 10, then I'm pretty certain that it's about 10%, but I have some uncertainty. It basically, yeah, it could be 5, could be maybe 18, but it's mostly it's centered around 10. So the red curve is our updated density of this random variable proportion. And so that's how Bayesian inference operates. It's a simple example, but it's really important to kind of understand and develop intuition for this example, because that's where it's happening, sort of in terms of that's every Bayesian inference kind of works the same way. It just becomes more complex and high dimensional, and lots of tricks and so on. But intuition is really the same in terms of how prior gets converted into posterior by data, basically by adding data. Okay, I'm out of time for the day. I will post the code that produced this plot so you can kind of look at this and understand what's going on. And then the Thanasi, Jesselyn, and Yevgeny, our three. Actually, no, hold on a second. Yevgeny just grading. Sorry, Thanasi and Jesselyn will be holding practice sessions. They are my PhD students. They're amazing, very friendly. They don't speak any Ukrainian. They speak only English. But they're very nice. So I recommend attending their practice sessions. I have a little bit of time if you have questions, but I don't want to delay you if you need to run somewhere. The question I have: why have we chosen a binomial beta distribution and not anything else? That's a good question. So for some of this we had choice. For some of them maybe we didn't. Binomial came into the picture here because of the. Oh, sorry, I didn't mean to do that. Right. So binomial came here because of the way we conducted the study. We conducted the study by grabbing people at random from a population and testing them. So that means I had basically for each individual was a little Bernoulli trial, which, coin flip, if you will, but biased coin with unknown probability of success. And so, so this binomial really came, it's a kind of mechanistic model of how we conducted the study. I didn't have a choice. I couldn't say, oh, it could be anything else. Does it make sense? The binomial is basically by construction, this is a binomial experiment. Beta is quite arbitrary. You're right about that. And so a beta distribution, we could have chosen something else, but to be honest, there's not a lot of nice, easy distributions that live between random variables that live between 0 and 1. So when we have probability or something that is, between 0 and 1, beta is just a very standard choice. You could construct something else, but it's just convenient, it's pretty flexible, and it allows us to encode prior information any way we want. So there's no reason to go to do something else, but you could do something else. So Bernoulli, sorry, Natalia, you're asking about Bernoulli formula in discrete one more time. Which do you mean all the way back before
Yes,
Bayesian or?
could you please explain whole that paragraph because I'm not familiar with that, unfortunately.
Sorry, do you mean this part or the paragraph or
Yes,
the?
yes, Bernoulli, binomial, and then you had a discrete paragraph.
Okay, yeah,
Yes,
this one. Okay,
yes, discrete random variables.
right. So yeah, so discrete random variables basically, when we define them, we usually define them by this little table. So for example, if I have a fair coin, right? A fair coin like this one, and I flip it 2 times, and I count how many heads I have, right? Like in this example. So I can assign probabilities like, oh, okay, this is all of these probabilities are a quarter, 0.25, because right, I need to flip a coin. Probability of head is 0.5, probability of second head is 0.5. The independent events, the product of 0.5 times 0.5 is 0.25, right? So this is now we defined right now a discrete random variable with 4 values, 2, 1, 1, actually 3 values. Sorry, I would convert it into 2, 1, and 0. And so I would have probability of 2 heads being 0.25, probability of 1 head exactly one heads, 1 tails, it's 0.5, and probability of 0 is 0.25 again. Notice they add up to 1. So this little table defines this random variable G that takes 3 values, and those are the probability of these values. And so this is typically how you can define this. Does it make sense?
Yes.
Okay, good. So basically, this is just notation. So for this, and you can binomial. For example, for Bernoulli, this table is very simple, right? So for Bernoulli, it's x. Sorry, I guess yes, and probability of x. And so Bernoulli, there are 2 possibilities, 0 and 1. probability of 0 is, sorry, too quickly. Probability of 0 is 1 minus p, probability of 1 is p. That's how we define it. This is the definition of this discrete random variable. I don't need anything else. For binomial, it becomes more complicated, right? I have more values. So for binomial, it would be x and its probability. And I would have 0, 1, dot, 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 up to n. And I would fill each of these cells with this formula, right? I would plug in k is equal to 0. Okay, plug in this formula, find this value. If I know n and k, I can plug in these values and find the numbers in this table.
Okay, thank you. It makes sense.
And so the kind of less intuitive is this continuous random variables because we need another object. So this is very intuitive, and that's how people developed probability back when Bernoulli brothers were alive and they were doing all of this for gaming and other things. But continuous random variables are also useful, and that's what we did right now. So continuous random variables are defined in terms of these objects that I just drew densities. So for example, in this case, what I was trying to say here that probability of my theta between values 0.05 and 0.2. Actually, I had this number somewhere, maybe. Oh yeah. So it turns out this is this area under the curve, and it's 0.66 in this case. So that's so this density is those are not probabilities, but you can convert them by probabilities by integration. So if you integrate this function between two values, that area under the curve, which in this case happens to be 0.66, that's the prior probability that our fraction of individuals was between 5% and 20%. So that's kind of a tricky object. These continuous random variables could be tricky to deal with because you don't have this little table, you have a continuous function, and you have to do integrals to recover probabilities from it. That's something I can suggest some further reading for that, but that's kind of the basically think of it as an analogous object. For discrete random variables, you have this little table. For continuous, you have these basically functions that gives you infinite number of values because we cannot have finite numbers, and that's why we don't have a table, we have a function instead.
Okay, thank you for explanation.
And yeah, of course, anytime. See, the integrals in the formula of the posterior beliefs must be definite, right? We integrate over real numbers. Yeah, it's a good point. I was probably a little sloppy. In this case, it's everything is yes, this integral is between 0 and 1 because we're integrating with respect to theta, and theta is between 0 and 1. That's why in this case, it's actually 0 and 1. It really depends on the domain of your parameter. If our parameter was a real number, any real number, it would be negative infinity, infinity. But in this case, our theta is 0, 1, so our limits of integration would be 0, 1. Yes, so there, you remember how does Bayesian statistics is related to this stuff? Well, the Bayesian statistics is actually what we just did. It's a very simple example of the Bayesian. We will do more complex, but we just performed the Bayesian inference for estimating proportion of something in a population, which you can do using frequency statistics. I encourage you to think about how you would do it from a frequentist point of view, from a regular classical point of view. But this is Bayesian statistics is basically based on probability calculus. You can, if you have some unknown parameter, you want to condition on the data, have a model, and then basically do this right here. So this is Bayesian inference, and that's how all of it is done. This posterior distribution of parameters given data, that's what makes it Bayesian when you condition on the data you observe. Of course, the situation can be very different. The models can be complex. You can do Bayesian inference for deep neural networks if you want to, which is as complex as it gets these days. But yeah, that's we just did a real Bayesian inference. Yes, iteration is a good point. Katarina is asking whether you can iterate. Yes, that's actually a very good point. You could say, okay, now this red curve is now my new prior. So when you do another study in Los Angeles, for example, you will use that as your prior and you will get more and more precise. Yeah. So Bayesian inference has a very nice sequential property. When you can sequentially add more data and become more precise. In the course on the course website, I well, I suggested that book. Sorry, my screen is blurred. Um, Bayes rules. So if you want to, of course, this course can only kind of, whet your appetite and make it, uh, or stimulate your curiosity about the topic. I don't have a lot of time to tell you lots of things that I would like you to tell you, um, but yeah, this book is really this Bayes rules book. It's a good one. It's free online, so the link that is already on the mini course website where I say that's how you set up your computing environment. So that already has a link to this book. Mina, one of the authors, Mina Dojo, she's my colleague here in Irvine. So she co-wrote it with other people. It's really good introduction to the topic. It's very gentle. It's not very sort of mathy. There's lots of, you can get as mathy as you want with these stuff. But it's designed for our undergraduate curriculum. So it's a first introduction to Bayesian inference. Yeah, Bayesian optimization is kind of a very different beast. I'm asking about Bayesian optimization. It's a quite a different topic. I mean, it has Bayesian ideas in it, but it is uh, not quite what we want to get at here. All right, I will have to run now, but it was uh, great to give this first lecture. I will update GitHub webpage, and you will get this GitHub link as well from in an email, because I'll add the code as well. So there will be a code that produced this figure, so you can play with the code a little bit as well. We'll play with the code next time, and definitely do it during the practice sessions.